So now we're going to talk a little bit about solving radical equations. And this will use the exact same skill set as simplifying radical expressions, but it will use it in reverse. So simplifying, remember, you start with the grouping symbol, then you deal with the exponent. Logarithms in a later chapter. So the exponent, which in this case is a radical. So you might wonder, why aren't radicals on here? Why isn't it called like GELMDAS or something? Radicals are exponents. So you deal with the grouping symbol, then the exponent, which is the radical symbol, then you deal with multiplication, division, addition, subtraction. But when solving, you do that in reverse. You're going to move any term that's on the wrong side when you try to solve using addition and subtraction. You're going to then eliminate any coefficients or negative signs using multiplication or division. You're then going to eliminate the exponent, and we're going to talk about how to do that. And then you would resolve anything in the grouping symbol starting from the bottom back to the top, which in this case, we actually have an example where you actually have to run through this twice. Please make sure that all answers are checked to see if they are extraneous, meaning they work algebraically, but do not balance the equation. So in general, what does an inverse mean? So the inverse operation is an operation that will cancel the original operation in any step of solving an equation. So for instance, the way you undo multiplication is to divide. The way you undo addition is to subtract. The way you undo the square root is to square, and the question is why? So more specifically, what is the inverse of a radical? For radicals, the inverse is to reciprocate the radical's equivalent exponent. So let's just take a little look at this. The square root of x is really, right, that's really x to the 1/2. That's the equivalent fractional exponent. So the inverse of that is to reciprocate that and use 2/1 or 2. That is why squaring a square root has canceled out, because you end up getting x to the 2/2 or 1. I know that's a long explanation to explain to you why it cancels, but that's what the inverse property does. Remember when you were much younger in math and you had to learn properties, and there was a property called the inverse identity property of multiplication, and that was like 3 times a third is 1. The goal of an inverse is to cancel out the original operation, which, remember that exponents are really a form of repeated multiplication, so we're going to be using the multiplicative inverse. So the way you inverse 1/3, which is the cube root's fractional equivalent, is to raise it to the third, right? Those will cancel, giving you x. The way you get rid of the 4th root is x, you change it to x to the 1/4, raising it to the 4th power, giving you x. It just makes good sense, I think. You know, all of these expressions here are equal to 1. And that would keep going if you had the 5th root or what have you. So what do you do if you have something like the 2/3 power? Well, you reciprocate this. Remember, that's why I wrote this longer version out here, so you wouldn't just think it was just whatever this is you put on the top. You have to reciprocate it. So technically this is 3/1, this is 4/1. So this would be reciprocated as 3/2. Notice I put a special little box there. We'll talk about that at the end. So this would give us x to the 2 times 3. Remember, the rule for for fractions is if you have multiplication of fractions, you multiply numerators with the numerators and denominators with denominators, and that would come out to the magic x to the 1st power, which means that we have used the multiplicative inverse. So we have done what we wanted to do. So for the 3/4 power, we would do 4/3, just reciprocate the original. That would give us x to the 12/12, which would give us x to the 1st. Again, that's the goal. And for 2/5, we would use 5/2, okay, which would give us x to the 10/10, which would be x to the 1st again. So the question is, why does that matter, right? Why did I put these in special little blinky boxes? And the reason is that's actually the square root. And you have to be careful about that. It happens right at this point. If I were solving, that's really, remember, if I were to go back and think about what that means, that's really the square root of x cubed. So when you take the square root, you have to include a plus or minus on the integer portion. The numerical portion would have to get a plus or minus. Very important to remember that. All right, let's take a look at an example of this in action. So in this example, this is a very basic example. There is nothing at the bottom of GELMDAS to do. There's no addition or subtraction or multiplication, division outside of the grouping symbol. They're inside of the grouping symbol here. So there's nothing to do other than try to get rid of the exponent. Well, these are both square roots, so I'm going to square both sides. And when I square both sides, well, all I have left is the grouping symbol left inside. So I have 2x minus 3. And believe it or not, I am down to a just basic linear equation on both sides problem from when you were in Algebra 1. So to figure this out, to solve this, you're going to get your variables on one side. So you're going to subtract 4x here and here. On this step, it was the inverse property, so we'll cancel it out. But here, this makes negative 2x. Okay, so we have negative 2x there. And then we'll go ahead and use this inverse property here. We're going to add 3 and add 3. And so it's kind of interesting because they both inverse. So the question is, what do you do? Well, this one, we'll call it 0, and we'll apply the inverse property there. So then we divide by negative 2, and we get, for our first equation, we get that x is equal to 0. Don't be afraid of 0. It is an integer. It is on the number line. The question is, does it work? So to determine if it works, you need to plug it back into the original problem and see if it's valid. So if I plug it back in, I would get 2 times 0 minus 3, which is the square root of negative 3. That doesn't exist, all right? That's an imaginary number. That's one of the reasons I sort of covered it, just so you understand that that does not exist. So at this point, we already know that this has no solution. Right, and to make it even more interesting, I did make it so that this problem actually has the same thing on the other side. So we'll talk about what that means. So if I put it on the other side, I would have the square root of 4 times 0 minus 3, which is also the square root of negative 3. And so a lot of students will say, hey, well, that works. Okay, that's why a lot of times you'll see no solution written as no real solution. And that's, if you've ever wondered why. And so that's probably the best way to describe this answer. There's no real solution. So even though this worked, it did not balance the equation over the integers, the real set of numbers. So that problem has no real solution. All right, so let's look at this one. This one has all the good stuff that you need in reverse GELMDAS. First thing we have to do is notice that we're trying to solve for this. This is our goal, this exponent. So we have to solve that initially by subtracting the 2 on both sides. When I subtract the 2 on both sides, I maintain my multiplication and my grouping symbol. And one thing that we have to remember in Algebra 2 and upper level math classes is we do not, okay, I repeat, we do not want to get to that step and do something crazy like try to distribute this in here. They do not distribute because they don't have the same exponent. Remember, the rule to combine bases is they have to have the same exponent. This has a 1 on it, so that does not distribute. It needs to be divided using reverse GELMDAS. All right, so that's the proper way to do that. Otherwise, you will basically have a problem that has a mathematical error, and you won't be able to solve the right equation once you make that error. Okay, so what we're going to do here is we're now going to reciprocate this exponent, and notice what happens here. I have that 2 on the bottom. See that right there? So when I do this problem, okay, I'm going to have to rewrite that so that we can actually try to evaluate. This just cancels, so I just have 3x minus 5. But here, the question is, what is this? Well, this is, remember, this is the exponent, so that is the square root, and then 4 to the 3rd power, right? And don't forget your plus or minus, because we just took the square root. So that'll be plus or minus 4 to the 3rd power, which is 64. So this right here actually comes out to plus or minus 8. What does that mean? Well, we saw this earlier when we had an absolute value equation. It means we have to set up 2 problems. We have to set up one in which it equals 8. So we have 3x minus 5 equals 8, and that's an easy enough problem to solve. And then we have a separate problem where we have 3x minus 5 equals negative 8, and then we'll want to check to make sure both of these work. So if I solve this equation, I would add 5 to both sides, And that would leave me with 3x is equal to 13, and then divide by 3, so x is 13/3, first answer. Same thing here, but when I add 5 to this number, I get -3, and then divide by 3, and I would get -1. Again, so what I did here was I added 5 to both sides, giving me -3, and then I divided by 3. So, you would want to go back and check them to make sure they work. And in this case, they both do. They're both valid solutions. So if you check this in here, if you take 13, I'll just do it arbitrarily. If I take 13/3 and put it in here, the 3's cancel. So you get 13 minus 5, which is 8. The cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12. 12 plus 2 is 14. So that works. If you take -1 and put it in here, you get -3 minus 5, which is -8. The cube root of that is -2. Then you square it and it becomes positive. That's why that plus or minus matters. So you have, again, -1 here, you get -3. -5 is -8. Cube root is -2. Square is +4. Times 3 is 12. 12 plus 2 is 14. So it works as well. So you just have to be careful about what you're doing. You can, of course, if you needed to, maybe use Desmos or type that into a calculator. All right, so in this example, we're going to do a very similar problem, but what's going to happen is it's going to change a little bit how the radical is used, how the reciprocated inverse of this will be used. So we are going to start the same way by reversing GELMDAS by adding 3 here. Again, we're starting at the bottom of GELMDAS, so we're adding and subtracting. Okay, that will cancel out this. Everything else will drop down. Do not distribute that 1/2. Remember, it does not have the same base or the same exponent, so there's nothing you can do but to wait to the next step. And we did addition and subtraction. The next step is going to be to use multiplication or division. So if we multiply by 2/1 or 2, that will get rid of that. And then 1 plus 3 is 4, so we multiply that by 2, and that will give us 8. All right, so over here it canceled out, and then I drop down the grouping symbol with the exponent, and again we're now at the step of GELMDAS to get rid of the exponent. I want you to watch carefully what happens, because the last one we had that plus or minus we had to deal with. But in this one, when we raise it to the reciprocal power of 4/3, remember 4/3 is a cube root. Cube roots don't have plus or minuses, only square roots do. So this will cancel out. It'll be 12/12. It will drop down, give you 4x minus 7, 12/12, which is 1. And then this will evaluate. So this is, remember, this is the root. So it'll be the cube root of 8. Okay, and then raised to the 4th power. The cube root of 8 is 2. And 2 to the 4th power is 16. So that's what that equals. And now we just solved this problem normally. Again, no need for a square root because there's no square, it's a cube root. So now we reverse GELMDAS again. Okay, so I add 7 to both sides. And 16 plus 7 is 23. And then we divide by 4. So this answer may look not very friendly to you, and that's why checking is so important. Because if you do check this, you understand why this is such a good number. Because if I take 24/3 and plug it back into here, the 4's cancel. So let's go over what that looks like. I know maybe in the last one I did a little, so let's just go over a little more detail. So 4 times this answer of 23/4. Again, you can use Desmos, but it's important to just try to understand what's happening to this numerically, or else the inverses and things, they sort of get lost on you. So watch what happens each inverse at a time. This inverse cancels here, okay? So then we get 23 minus 7, and 23 minus 7 is going to be 16. So we have 1/2, 16 to the 4th 3/4, and that is going to be the fourth root of 16. So the fourth root of 16, which is 2, and 2 to the third power is 8. So we have 1/2 times 8 minus 3. 1/2 of 8 is 4. 4 minus 3 is 1. And of course, you can do that on a calculator or Desmos, but it sure does help you understand all of the important small details that make you good at math to go through that by hand. And you can see that it is supposed to equal 1, so that does in fact check. All right, so what happens in this one, and why do we have this extra example? There is nothing to add or subtract. I mean, you could add or subtract this over here, but then it doesn't help you. Remember, the goal is to solve for the grouping symbol, which is already solved already. So nothing to add or subtract, nothing to multiply or divide. So what we're going to do is square this on both sides and understand what that does algebraically. So here, this square and this square root, they will eliminate each other because they're inverses, giving you 4x minus 3. But over here, we end up getting this squared, which means that we have x minus 2 and x minus 2, which means we have to maybe make a box to figure that out, right? We can't just say that that's x squared minus 4. It's being foiled together. So x minus 2 will go here, and then here we'll have x minus 2. X times x is x squared. Negative 2x, negative 2 times x is negative 2x. Negative 2 times x is negative 2x. And then negative 2 times negative 2 is 4. And so this here will come out to x squared. Remember, the combined like terms always comes out on the diagonal. Minus 4x, and then plus 4. So now we have, for the first time, a quadratic. So how do we solve a quadratic? What's the process? It remains the same. It's reversing GELMDAS. We need to group for the exponent. So we're going to get rid of this by adding it to both sides. The goal is to set it equal to 0 when you have a quadratic. Okay, so this will cancel, giving me 4x. Actually, we can do all that in one step. I don't want to make anybody too scared, but that just cancels. So to save some paper, why don't we subtract 4x over here to this 4x. That'll cancel here, giving us 0. That is the goal for a quadratic. This is x squared, drops down. Negative 4x minus 4x is negative 8x. And then 4 plus 3 is 7. So believe it or not, we've done the addition and subtraction step. There is no multiplication step. The multiplication step in a quadratic is actually GCF factoring. So there is no common term, but what we do have here is we have what's known as just regular old A lead coefficient 1 factoring, which is fairly easy. Let me show you how easy it is to factor in this world. If you have an addition sign, you either have double plus or double minus, because 2 positives make a positive and 2 negatives make a positive. So in this case, it's double negative because this tells you what it is. So if this were positive, it would be 2 pluses. If that's negative, it's 2 negatives. Because remember, a negative times a negative is a positive. So then you factor this out from like the factors from third grade multiplication tables. This is just 1 times 7. And so we're actually done because 1 times 7 is 7. And now we're trying to add this, right? We're trying to add these factors to get 8. So 1 and 7 multiply to 7, and they add to negative 8. Now, unfortunately, that's just a process. That's not the answer. The answer is to now solve this. And you may remember from Algebra 1 that you would set both these equal to 0. So if I add 1 to both sides, my first answer is x equals 1. And if I set this equal to 0, this will give me x equals 7. So the question is, do both of these work, right? You do need to check them. They're not that hard to check. Let's put 1 in here. So I would get, if I put 1 in here, I would get 4 minus 3. That gives me the square root of 1. And the square root of 1 is 1. Do I get the same thing when I put it in here? Over here, I get 1 minus 2, and 1 minus 2 is negative 1. This is an extraneous solution. Extraneous means this. You've created mathematical balance, but that balance, right, it's the same quantity, but it's not the same value. So it balances the equation, but when plugged back in, it doesn't satisfy the original problem. Let's see if 7 does. So if I put 7 into here, I would get 28. So I have 28 minus 3. That would be the square root of 25, which would be 5. Okay, and if I put 7 into here, into this expression, I would get 7 minus 2, and 7 minus 2 is in fact 5. Notice this is the same quantity and the same sign, so that does check. That's my only answer. This one was extraneous, this one is valid, meaning when I plugged it in, it gave me the same thing on both sides with no mix match of sign.